K nearest neighbors is a simple algorithm that works by finding the nearest K neighbors of a data point from a training set. One of the questions you should ask yourself when you're learning about a new machine learning model is, when can I apply this model? In other words, can I apply this model for supervised learning or unsupervised learning? And specifically, can I apply it for regression or classification? The K nearest neighbor algorithm can be adapted for both regression and classification. So let me quickly illustrate what's going on with K nearest neighbors. Let's say we have a two-dimensional space, and one of the important concepts we'll be making use of when we start analyzing these models is you can view that our data set, our feature matrix, exists in a p-dimensional space, where p is the number of columns, the number of features, characteristics, degrees of freedom of our data set. In this example here, we just have a two-dimensional space. And let's say we just have, I'm going to just put random points in here. Random points, so these are our training examples. And one way you can view K nearest neighbors as some sort of interpolation technique. So if I say, let me go ahead and predict some value for an observation, and I'm going to say, let's say right there, my point exists right there. Then what I can go ahead and do is that if I want to predict something for this observation, what I can go ahead and do is I can look for its nearest neighbors. Which points is it closest to? And I need to set how many neighbors I'm going to use for my prediction. For this example, I'm going to set 3, so give me the 3 nearest neighbors. So this algorithm will look up and find that these 3 points are its closest neighbors. With those 3 nearest points, then I can use it to make a prediction. Now let me throw this question at you. If we are doing regression, what would be a natural choice? What would be a natural choice to use to calculate some continuous value for our observation using our, in this case, our 3 nearest neighbors? We can use the mean value of our 3 neighbors to generate what is our predictive value for this observation. So you can see how it can be viewed as an interpolation technique. What about for doing classification? Taking our K nearest neighbors, whatever they are, in this case it's just 3, how can we take our K nearest neighbors, and how can we predict what class does our observation reside in? What we can do there is we can just do a popularity vote. In this example here, we only have 3 neighbors. So let's say 2 of those neighbors are in class 0 and one's in class 1. Then since class 0 is the majority amongst the neighbors, we can go ahead and label this observation as being in class 0. So we can see what is the majority class amongst its neighborhood, in its neighborhood. Now, one of the things about classification algorithms is we want to ask ourselves, will this algorithm naturally handle multi-classification? Remember when we studied logistic regression, one of the limitations, at least an initial limitation of logistic regression, is that it's a binary classifier. However, there was those techniques we discussed where we can extend logistic regression, and it can be used to handle situations where there's more than 2 classes. But in K nearest neighbors, do we have to do any of those techniques, any of those additions, model modifications to handle multi-classification? What do you think? Or do you think it can naturally handle more than 2 classes? It's going to be able to handle more than 2 classes naturally. It's going to apply the same situation. Amongst its neighbors, which of the classes was the majority? Which one had the most votes? So you can see when we're talking about k nearest neighbors, we're making use of the idea of finding neighbors. Now, how do we go about finding neighbors? How should we find neighbors in our p-dimensional space where our data resides in? So we have to devise a distance metric. We have to calculate the distance from our observation to all the training points that we're using in our method. So we can define a distance metric here. And we can use naturally the Euclidean distance. But we don't have to use the Euclidean distance. Remember the Euclidean distance, how it works is that you find the difference. Let's say you're trying to find the distance from point A to point B. You subtract their components, their respective components. You square the differences, and you sum them up, and you take the square root. That's the Euclidean distance. And of course, you can do this for any number of dimensions, not 2 dimensions, not 1, 3. You can do it for higher dimensions, whatever number of dimensions we have for our example. But as I said before, we can generalize the idea of distance and not use the Euclidean distance, which uses a square, but we can use any power p. And this generalized distance is called the Minkowski distance. So we can modify our distance metric to be as general as possible, such that it takes a parameter p. And of course, when p is equal to 2, it just falls into the standard Euclidean distance. Since we have control in which what distance metric we should use, how should we treat this parameter in the model? What would we call this parameter in our model if we can have some control over it prior to the fitting process? It's going to be a hyperparameter of the model. You can go ahead and set what should be the power for this Minkowski distance. Now let's talk about when we calculate distances with this model. For a lot of these models, we must ask ourselves, do we need to scale our features? Do we need to scale our features, and will that help our model's performance? So what do you guys think? What are your thoughts? Do we need to scale our features to use this model? Well, let's see what happens if we don't scale our features. If we don't scale our features, we might have a situation in which a bulk of, let's say, x1 is going to only vary within this small range, but the other feature is going to vary over this larger range. So when we calculate distances, one of the things if we don't scale our features, we might bias our algorithm's usage. We might say that one feature is more important because it exists in a different scale. So we have to renormalize our data set, renormalize our features such that they all exhibit within the same scale. So we'll go ahead and transform this such that they have the same scale. So when we use k nearest neighbors, we have to scale our data. Remember, the variations along x1 are so much less than the variations of x of 2. So it might preferentially pick neighbors based upon how close the x of 2. So it's biasing, it's focusing too much on x of 2 as opposed to x of 1 as opposed to x of 2. So we need to scale our data. So we can do that via standard scalar. We've seen how that works out. Okay, so the classic example that people like to use to illustrate k nearest neighbors algorithm is by using the iris data set. So this is a famous data set. So it's about 150 observations, and it's for classification. And the task is, can you take different measurements of the flower of an iris to classify what species does this flower belong to? Those four characteristics are the petal length, petal width, sepal length, and sepal width. So we have a four-dimensional problem. And for this case here, let's go ahead and just use two features for our data. So we're going to load the iris data set. We're going to take the x and y. We're going to scale our data. Then we're going to have a function here to interact, to create an interactive plot where we can visualize our model's performance. Okay, I forgot to run this 2 lines of code here. Okay, so there it is. So here we have our image. What am I plotting here? We've seen a very similar plot like this before. What am I plotting here? Well, I'm plotting the decision boundary. Remember we did that for logistic regression? Here we have the decision boundary for our k nearest neighbors classifier. So we have 2 dimensions here. Notice we've scaled our data so it has a similar range. And we notice that the regions in purple belong to the purple class. Regions in green refer to the green class, and regions in yellow refer to the yellow class. So we can see, given some other observation that we could have in our space, what would our model predicted?